Hello and welcome to the iSystem webinar series. Today's episode is about how to avoid dead code, on-target code coverage measurement with iSystem tools. You will learn about the different types of code coverage and see a winIDEA live performance, as well as how the automation works. My name is Sabrina Kisslinger. I'm the moderator. Today's speaker is Anja Wisnica, who will lead you through the technical presentation. Anja is software test engineer at iSystem, focusing mainly on regression testing. She spends her time writing and running tests as well as developing embedded applications for testing purposes. Anja participated on tool qualification projects for DO178C and is familiar with ISO 26262 as well. Before we start, I would like to give you some general information. During the webinar, you will be muted. If you have questions, please use the question tab in the menu bar. Below the question tab, the handout tab allows you to download the presentation. Today's episode will be recorded and published on the iSystem YouTube channel. At the end of the webinar, some of your questions will be picked and answered by Anja. All others will be answered by email afterwards. So that's it from my side. Over to you, Anja.
Hi Sabrina, thanks for the introduction. Today I'll be taking you through this code coverage webinar. And by the end of it, I hope you'll be able to know which types of code coverage analysis are possible with iSystem tools. You'll understand how it works under the hood. You'll be able to record trace and perform coverage analysis and export all of that into the HTML report. And you'll also be able to do all of that using our iSystem Connect SDK. First things first, coverage analysis that we're talking about today is performed on a trace recording. I'll just assume you're familiar with the hardware trace. However, if you're new to tracing, please check Introduction to Tracing webinar. Felix explains various trace possibilities and demonstrates how trace is recorded in winIDEA. Now let's quickly go through our plan for today. I know most of you are probably familiar with coverage, but just in case we have some beginners with us, I'll quickly go through the types of code coverage available with iSystem tools. Next, we'll look how iSystem performs coverage analysis, particularly how code coverage is measured on the object level. After that, I'll show you how this is done in winIDEA. We'll record a trace, perform the coverage analysis, and export it into HTML, and we'll go through the report together. In the end, for more advanced users, I will show how this can be done with our iSystem Connect SDK as well. Finally, I'll answer a few of your questions, and the rest I'll get to over the email shortly. I'm sure most of you know what coverage metric is, but just to make sure everybody is on board, we measure code coverage to see how thoroughly our application has been tested. If the code coverage is 100% after the tests are done, this means that we've tested the application well. If the code coverage is 50%, that means only half of the application was in fact tested. There are different types of code coverage metrics available. I will not go into details about what types of errors are detected by different types of code coverage metrics. You can find that information online. Suffice it to say that for a simple function coverage, all you need to know is that each function has executed. But if you would wish to do a statement coverage, that means that every source line in every function needs to be executed. That already means that you will have to generate more test vectors to cover all of that. Usually the standard to which your project is complying, such as DO178C or ISO 26262, will dictate the type of coverage that needs to be measured. The more safety critical the project is, the more complex coverage matrix will be used and more test vectors will be required. Now let's look at different types of code coverages available with iSystem winIDEA: statement coverage, function coverage, call coverage, branch coverage, and decision coverage. First, let's look at the statement coverage. Statement coverage is concerned with source lines And to achieve 100% statement coverage, you need to make sure that all the source lines in your code have been covered. I have marked the source lines with the blue dots here. Next, let's see what function coverage is. Function coverage is concerned whether each function in your application has been tested. So we have two functions here, my function and the sum function, and in order to achieve 100% function coverage, both of those functions would have to be called at a certain point in the tests. Next, we have call coverage. This differs from the function coverage in a way that it checks that every function call has been executed. So in this case, we see that the sum function was called twice. And in order to achieve 100% call coverage, both of those function calls would have to execute. Next, we have branch coverage. This coverage metric checks if every branch in your application has been executed. So in our function here, we have an if statement that branches into possible ways depending on the condition outcome. So to achieve 100% branch coverage, both of those parts of the code would need to be executed. And for the last, we have decision coverage that checks that each decision in the program has evaluated to true and false. It's considered with the decision as a whole, not by different parts of the decision. And here we have two such decisions. One is a ternary operator that conditionally assigns value to a variable c, and the other is the if statement. Note that it has two conditions, but the decision coverage is concerned with the decision as a whole. So to achieve 100% decision coverage in this case, both decisions would have to evaluate to true and to false. C would be assigned A and B, and the if statement would execute this way and that way. Now it's time to take a look at how iSystem measures coverage. winIDEA doesn't need any code instrumentation. Instead, it works from a hardware trace recording. Most of the modern microcontrollers are able to produce information about how the program is executing. We won't go into details here, as my colleague Felix has already covered this extensively in the Introduction to Tracing webinar. I'll provide the links later on and you can check that out. What you need to know is that compressed program flow data is extracted from the microcontroller and uploaded to the PC by the BlueBox. winIDEA then takes the compressed information and cross-references it with the information about the application that is available in your download file. Based on this information, it reconstructs the actual program flow. We call this a trace file. Coverage and other analysis are then performed on the trace file. Note that we're working with the information on the level of object code instructions, which differs a bit from the standard source code approach. I'll get into the differences a bit later on. In the trace data, we have two relevant types of information: which instructions were executed, and in case of conditional instructions, how did the condition evaluate at the time of execution. So here on the right, you can see my function, the function we've been seeing earlier as well, in its disassembled view. And you can see the instructions within it. And additionally, the red ones are the conditional instructions. So for regular instructions, you would just have the information whether the instruction executed or not. And for the conditional instructions, you would know whether the condition evaluated to true, false, maybe the branch didn't execute at all, or perhaps it executed twice and we have covered both branches. Instruction coverage is marked with green and red squares, and it tells you whether the instruction executed or not. This type of coverage is also measured on the conditional statements, conditional instructions, but the graphic is a bit different because it conveys more information. So for conditional instructions, we know that If both arrows are red, that means that it did not execute at all. Then if one of the arrows is green, it means that it either evaluated to true or to false. And if both arrows are green, that means that it evaluated both ways. So it executed twice or more times, and it evaluated it true as well as false. However, we don't want to waste too much time looking at the opcodes, so winIDEA offers a view on the source level as well. Each source line has a range of instructions that are generated by the compiler. The range of these instructions for each source line is stored in a debug section of the ELF file. winIDEA shows squares for each source line that has some object code associated with it. For example, here you can see the object code belonging to the source line. You may also notice that there is a square on an opening bracket. This is usually function prolog generated by the compiler. Each such square will be considered for code coverage. Once we know which instructions belong to the source line, we merge the object level coverage to show it on the source level. The statement coverage is easy. If the instructions within that source line executed, it is covered. If they did not execute, it is not covered. Conditional statements are a bit trickier as they merge the information of all the conditional instructions in its range. For example, here we have two conditional instructions belonging to the source line, and you can imagine as if we put each coverage outcome of each conditional instruction on top of each other, and the red light shines through. In this example, we see that this branch did execute once, but this one didn't execute at all. And to indicate that, you see that both arrows are red. That means there is at least one conditional instruction that did not evaluate to true and at least one that did not evaluate to false. If you see this symbol, it means you need to dig deeper to see what happens. And where winIDEA really makes sense, it's on the object level. While this might not be very intuitive, it is, however, very thorough, much more than a regular branch coverage. Okay, now that we've covered this, let me open winIDEA and show you code coverage in action. Okay, now that we have opened winIDEA, we will begin by establishing a debug session by downloading the application to the microcontroller. I will do that by clicking the download button. For the sake of simplicity of this demo, I will focus just on a tiny bit of the application. So I will set a breakpoint here and run until I hit the breakpoint. Okay. Next thing we need to do is create the analyzer file, and you can do that by clicking View, Analyzer. I will bring this window up here so it's easier to see. And first we will need to set the configuration. By default, the configuration already includes coverage analysis, but let's go through it together just in case. So, as you can see, by default we have enabled profiler and coverage analysis. I will disable the profiler analysis as we're not interested in it at the moment. And then let's see the coverage tab. Here we can see that the scope of the coverage analysis is all downloaded code. You have various options to limit this if needed, but at the moment for our example this will be good enough. We will include everything as well as the assembler information. Let's press OK. And now we are ready to begin the analyzer session and start the coverage analysis. We do that by clicking the Begin New Session button, the green play button. And you can see that the analyzer is now in the waiting state. As soon as we run the microcontroller, the trace recording will begin, and once that is recorded, uploaded to your computer and then analyzed, you will see the coverage information. So let's continue by running the CPU. And you can already see the coverage information right here in the editor. You can see that the recording was successful. But at this moment, we will focus on our TRD file, on the trace file. And here you can see the coverage statistics window. We also have profiler timeline window, which we don't need at this moment, so I will close it. If you ever lose the coverage statistics window, you can always bring it back by clicking the coverage statistics button right here. Now let's look at some of the configuration options for the coverage analysis. You can do that by clicking the options button. And here we have already focused the coverage tab. There are several options available. If you click on them, you will see the descriptions of what this option does. But at the moment, we're only interested in this option, show verbose text. And this will make the report easier to read. Okay. And as you can see, the text became a bit longer and clearer with this option enabled. Now you can see that we already have all different types of coverage analysis supported by iSystem tools available in this view. So let's drill down to see the functions that we are interested in. So we select our download file, the folder where the module is located. Yes, the functions are within the main module. Okay. So here you can see we already have statement coverage written for all different levels you might be interested in, but at the moment, let's look into my function. We drill down further and we can see that it includes 8 lines, 5 of which were covered. If you remember, this function includes an if statement, and since we already only executed this function once, only one branch of this if statement was executed. So therefore, not all the statements were covered. And this is obvious from this view. You can see that 3 lines were not covered. And therefore, we have 5 lines out of 8. That gives us a 63% coverage, statement coverage. Similar can be seen on the object level. I have just hidden this out of the view so we can focus on the next item. So we can also see this on the object level, where instead of source lines, we're dealing with instructions or the object code needed for those instructions. Very similar view. Let's hide this as well. Now we get to the good part. Now we have the condition coverage outcomes. If you remember earlier from what I was talking about, this requires a bit of the understanding on the object level. Let me expand this. Okay, so here you can see that we have 2 conditional statements, an if statement and the ternary operator. But here you can see that within my function we have 3 conditionals. This can be easily explained if we look deeper. And here in the if statement you see we have 2 conditions. And the way compiler solves this is by creating 2 conditional instructions through which these conditions are evaluated. So all in all, you can see we have 3 conditional instructions. 1, 2, 3. And this is the 3 conditionals that are accounted for in my function. Now further, each of these conditionals can evaluate to true or false, or ideally both, to achieve 100% coverage. In our case here, we can see that some of them evaluated to true and 1 evaluated to false. Those are 3 different outcomes possible out of 6 possible outcomes 2 for each conditional, which in total gives us 50% condition coverage. Okay, let me hide this. We're not interested in execution calls at the moment. I will hide this as well. Okay. Next we have call coverage. As you can see, in my function, we have 2 function calls. We're calling the sum function twice. However, in the report, you see there are 4 function calls. So how did this happen? The hint is hidden right here. You see there is 1 call hidden in a function prologue. And if we expand this, we see there is a function call to save general purpose register function. This is part of the compiler provided library. And 1 function call is also hidden in the function epilogue. And this is restore general purpose. And this is restore general purpose registers. So all in all, we have 4 function calls. 1, 2, 3, 4. And as you can see, 3 of these were executed. This one did not, as that part of the if statement did not execute. And now at last, let's look at the function coverage. And on the level of the main module, you see that we have 3 functions, main, my function, and sum, all of which were executed, and that gives us 100% coverage. However, you might notice that main function has a red square drawn, and that is because we didn't really execute all of the main function. We just executed some part of it. We didn't even record the beginning of it. And this indicates that something odd happened. The beginning of this function is missing. It's still considered covered because we did execute it, but if you're interested in this amount of information, you can also see it in this level. Before we wrap this up, let's document this session and write some information about it. We do that by clicking the Set Information button. Now let's write the name for our session. Let's come up with a fictitious ID. We're testing my dummy application. And we're performing the tests on the MPC. Let's add a comment to it. Okay. Now I will save the file. Now that we're familiar with how coverage output looks like in winIDEA, let's export this into HTML report. You can do that by clicking the Export Coverage Results button. By default, the HTML export is already selected and the default configuration is quite alright. Maybe I'll just select that we're interested in all the code. And I will also add the disassembly information to the coverage report for the sake of clarity. And let's export. Okay, now let me open the report. Now this is the entry point to the HTML report. And as you can see, it has all the information that you have added for your test run. In addition to the top level view of the coverage, the statement coverage and conditional coverage. You can see that the coverage is really low. We have only covered 6% of the whole application statement coverage. And that's because our test was really small. It just focused on a couple of functions instead of the whole application. So this is to be expected. Now we can drill down to see more details. On this level, you can see we have 3 different folders. and one of them is from the compiler provided code, and 2 of those are ours, so the core code and the common code. And the part that we were testing is in the main module, so I will focus on this. And there are 2 options. You can either click on main module to see the functions within it, or you can click on the source link to see the file directly. So this view is very similar to what you are used to in winIDEA. And you can see that it contains 15 source lines that generated code, so that equals to the amount of the colored squares. The source lines that do not generate code are not considered. This information is obtained by winIDEA from the debug information, and you will see squares every time where the compiler says there is code generated for this line. So here we see that we have covered 11 out of 15 such source lines. Next, we have condition coverage. We already explained earlier that this is best understood on the object code level, so let me open this up. You can see the details by clicking on the coverage outcome button. And here we can see the 3 conditional statements that we've identified earlier. And as I've said before, each of these 3 conditional statements can have 2 possible outcomes. That makes a total of 6 possible outcomes, and 3 of which were achieved during the test. You can see very clearly now how this icon, 2 red arrows, translate to actually 2 conditional instructions, each of which has evaluated differently. And since not all of the branches were covered, this is the indication for it. Now let's go back. As you have seen, you can navigate through all the through your download file and through the folders that compose it, and the modules that compose it, and the functions, and you have all these different views available. But there is one that I would like to show you, and this is untested code. This will come in handy when you achieve less than 100% coverage and you need to investigate what happened. So here we can see that obviously we didn't test the compiler provided libraries fully. That's to be expected, as our tests were not exhaustive as it is. And based on the review, you can decide whether you need more tests. For example, you've identified part of the code that you forgot to test, or there could be a part of the application that can never be reached. For example, if you have an if statement with a very complex condition, it could happen that it can never evaluate a true. That means that part of the application will never execute. And in that case, you have just found that code, and that's a prime candidate for a cleanup. Okay, so this is basically it, what I wanted to show on our report. Next, I would like to show you how to achieve all this using our SDK, iSystem Connect. Okay, now that we've seen how this is done in winIDEA, let's see how we can achieve the same thing using iSystem Connect SDK. For scripting with it, you'll need iSystem Connect SDK. Once you install winIDEA, Python and matching iSystem Connect SDK is already available in the installation folder. You can use that for your first steps into iSystem Connect. But if you plan to integrate this into your testing suite, then I would suggest that you download SDK from web page. We support various programming languages, and you should use that instead. First of all, you'll need to import iSystem Connect module, create a connection manager, and connect it to winIDEA. This will launch a new winIDEA instance if it's not already running. This is something you'll see a lot with our samples. Next, we need to create controllers that we'll need. In our example, we need a debug controller. We'll use it for running and stopping the CPU. And we'll need the coverage controller. This one we will use for recording trace and performing coverage analysis. Note that this will create an example TRD document in the workspace folder if it doesn't exist yet. And then to begin everything, we will establish a debug session by performing a download. As you can see here on the right, I have written an example script that we'll be going through together chunk by chunk. And next we need to create a fresh trigger configuration and select it. This is in the lines 14 to 16. We'll be working with default analyzer configuration in this case. Next, we need to set the scope of the coverage analysis. In our case, we'll analyze all downloaded code. Now we're almost ready to start. If the document was freshly created, it's already ready by now. But if the file already exists and contains a huge chunk of trace data, it might require a few seconds or more to load. So we will just wait until the file is loaded. Now we're ready to start recording. First, we start the analyzer session, and then we run the CPU. In this case, we're letting the CPU run for a second, but you can easily adapt this to whatever is needed in your project. And when the test code is done, we will stop the CPU, which also stops the analyzer session. So now let's make sure that the CPU is in fact stopped. Sometimes it takes a few moments. And then we wait for the coverage data to load. This waits while the trace information is loaded from the target to the PC. Make sure you don't skip this step, as you can still export the data even if it's not fully loaded yet, but you'd be missing a lot of information and will achieve lower coverage because of it. Now that we have the recording, it's time to export it to XML. XML export is required to access the coverage data from within the iSystem Connect SDK. So I've created an export configuration here where I set the XML file name and set the scope of the export. I will export everything available, while you might configure this to your needs to save on time and space. Once we export the data, the XML file will be created in the workspace directory. To access the coverage data, we need to import the XML document into coverage data 2 controller. I've shown this here. Make sure to check for warnings. If anything went wrong during the trace recording, this will notify you. Close the parser once you're done using it. And finally, at last, we're ready to read the coverage information. We'll create an iterator. Iterators are used to improve performance when working with huge data sets. In this case, we're iterating through functions. For each function, we print the area name. In this case, this means function name, and its statement coverage. But yeah, this is it. Here I have a small screenshot on how this output would look like in our example. And this is it. And this is how you use iSystem Connect SDK to get coverage data. You could also use this to export, to create an HTML export if you wanted to. I just wanted to show an additional step on how to parse the coverage information within the SDK. And this is it for today. Once you start integrating iSystem tools in your process, you will want them to perform as best as they can. And to do that, I'd like to share 2 tips with you. First, make sure that the data is streamed from the target to the PC without hiccups. There are many possible bottlenecks, from poorly designed target layout to poorly performing disk on your PC. If you're using a trace port and everything is optimized, it is possible to record a trace for days at a time. Tips on how to do that can be found in winIDEA help. I'll leave a link here. And last, if you're facing limitations, for example, your microcontroller doesn't have a dedicated trace port, but just an on-chip trace buffer, you need to make do with what's available. In that case, you can use triggers and qualifiers to focus on a specific part of the application and perform the tests and coverage measurements part by part. Later on, you can merge the coverage information into one complete report. Links to online help and tutorials on tracing are linked here as well.
Thank you, Anja, for your demonstration. Let's continue now with the Q&A session. Several questions reached us, so I'd like to pick quite different ones. The first one is the microcontroller we are using does not have trace. Can we still do code coverage with your tools?
Okay, so in that case, you still have a few options. The easiest one, the most convenient one would be to use an emulation adapter. This comes in handy if your device has like a superset package. So for example, your device doesn't have trace, but a bigger device exists that has trace. And in that case, we can make an adapter where we can you can load your application on the adapter, and it's executing on our adapter, but all the pins, so the same layout as you would have on your microcontroller, is routed through an adapter board, and it's connected directly into your hardware. So everything executes the same as if you had your regular microcontroller present there, but you get the trace benefits on top. I know this is possible on tri-core devices, that's possible on Chorus devices, but you can send an email with your specific device to see if we have such an emulation adapter available. And if it's not available, then there is still one option that's not so ideal. It's called slow run. It's slow, as the name implies. And it's only useful on a small scale. And what it does is that your application is not executed in real time, but we effectively step through the application instruction by instruction and record the program flow that way. The interrupts are disabled in that mode, so that means you won't be able to perform your regular tests with it because your application probably relies on interrupts. But it's useful for unit tests, for example.
One thing I'd like to add here from a tooling perspective, for performing the code coverage analysis, your debugger needs to be equipped with a so-called trace activation key. You can check that if your debugger has this enabled in the winIDEA menu bars, in the winIDEA menu bar tools license. There you can see the configuration. If you have a trace activation key, if you don't have one, your iSystem contact person will help you to get one. So let's come to the next question. How about MCDC? I didn't see that on the list.
Yes, so MCDC is a little bit special. So it's defined on the source level. And so you basically need to prove that by changing an outcome of a condition, you can change the outcome of a decision. And we cannot do MCDC with our tools. This is because it requires awareness of decisions and conditions on source level. So our tools rely on what is available in the debug information, and this type of information is unfortunately not available at the moment. So we cannot make any conclusions about the MCDC coverage based on the object code coverage that we are doing with our tools. However, there is I've seen research done on this topic, and our approach is called object branch coverage, but in some cases. And the CAST team, Certification Authorities Software team, has analyzed this approach in comparison to MCDC. And what they found is that if you're using simple decisions, like maximum 2 conditions, In that case, both coverage metrics are comparable, and you could use object branch coverage instead of MCDC. But if your application is more complex, so it uses decisions with 3 or more conditions, then MCDC is better, and you're no longer allowed to use our approach instead. If you're interested in this, in using object branch coverage instead of MCDC, I suggest you check their position papers. There are 2 that are relevant for this topic. One is CAST -17 and one is CAST -12. Both are available on the FAA webpage, and you can see all the steps that need to be undertaken if you wish to use this instead.
Thank you, Anja. The next question came in from different attendees. So several people were asking if it's possible to measure coverage with specific devices. People were asking about Tricore and RH850. So how about that?
Sure, it's possible to measure coverage. So on RH850, ideally, if you have a device that has a trace port, then this is trivial, and everything that I have explained earlier still applies. But if you have a more limited device that has only an on-chip trace buffer, this is a bit trickier because the size is too small to record for a longer period of time. There is one trick that we can use here, and it's called stumble mode. What it does is that when the trace buffer is full, it stops the CPU, and it then pumps the information from the trace buffer to winIDEA, to the PC. And when the upload is complete, it resumes your application. So the application will run and stop and run and stop. It will take a bit longer. It won't be exactly real time, but if timing is not a consideration, which is usually not for coverage measurements, this can be still used to get longer coverage recordings. Then for Tricore, the best is if you have a device with Aurora trace port. There are a few available, and that is the best. But if you don't have that and you only have an on-chip trace buffer, then there is a special approach that we use. It's called upload while sampling. And what it does is it uses the on-chip trace buffer, which is usually composed of several emulation memory tiles. And we know when one tile is full. And so as soon as one tile is full, we start uploading that to the PC, and the trace recording continues on the other tiles. And so if we are able to upload the information faster than it's being generated, this could go on indefinitely, but usually that's not the case. It just prolongs the session, and you will still probably have to record several chunks and then merge those together. Maybe I'd like to point out a few things that you can do to prolong the time that you can record coverage. One is to use our IC5700 with an active probe, because that can reach much higher frequencies. We can use 160 megahertz. That is if your hardware design supports that speed. So that will really help. If your device supports 2 channels, so DAP and DAP-E, then DAP-E channel can be used to upload the trace independently of any other communication we have with the microcontroller. You could also record 1 core at a time, so to limit the amount of information being generated by the microcontroller. Then if you're a more advanced user, you could also create a manual trigger. In that case, you can disable the timestamps. Timestamps do take a lot of space on in the trace buffer. So if you disable that, the recording will last longer. But yeah, it takes some fine tuning to get longer sessions in this case. So as you probably will have to record several chunks, you will then have to merge everything together in one report. And I didn't cover this in my SDK example, but you can Google coverage merge.py iSystem, and you will see an example how this can be done to have one single report for all the different parts of the trace recording that you have to record.
And of course, not also RH850 or Tricore, but also the ARM S32K1 is also possible to do some code coverage here, depending on the exact derivative, of course. And Anja, one question regarding the SDK just came in, which I would like to add here. Can I generate an HTML report using the SDK?
Yes, it's definitely possible to do an HTML report. I think there is an example available online as well, but if it's not, I'm gonna send one to you.
Okay, thank you. So no more questions. Thank you, Anja. Let's come to an end now. If you have questions, please feel free to send them to us. And before you leave, I would like to give you some additional information. Do not forget to download the presentation in the handout tab of the menu bar. Check out our free online trace tutorial, our YouTube channel where this webinar will be hosted, and others are already available. And if you want to, feel free to register for our newsletter to get interesting updates automatically. If questions come to your mind later, please feel free to send an email to webinar@isystem.com or your known iSystem contact person. Thank you for attending. Please fill in the feedback form after leaving. Bye and take care.